All right, it looks like we are now recording. Hooray! All right, good job. So this morning, let's start with, it's essentially going to be a second example of how a character table is built. And we're going to be looking at character tables in much more detail today and next class. And we tried to build one by looking at all the symmetry elements of water last class. And I'm sure it came across as a little bit confusing. And so let's go through another example, which is on the back of the homework worksheet that you had for today. So we'll consider the D3 point group. So any molecule, regardless of what the molecule would be, any molecule that's in the D3 point group has only three symmetry operations. It has E, which everything always has. It has a C3 axis and a perpendicular C2 axis. So those would be the three elements that you could identify. Right? So in order to construct the character table, we want the transformation matrix for each of these operations. And these were the 3x3 matrices that we looked at the other day, because they're going to transform or show us how the coordinates of an atom in this molecule change upon operating on it with one of these operations. So the E transformation matrix is the easiest one. It has just ones down the diagonal, because it does not change the coordinates of the molecule at all, or of the atom. It leaves everything alone. The C2, we looked at this one in class last time as well. The C2 has diagonal elements -1, -1, 1. Now we kind of developed this intuitively by playing with the water molecule. But in reality, remember, this can be predicted using the sort of the generic transformation matrix that I showed you, involving sines and cosines of the angle. Sorry, this is C2. I'm doing it, just realized, a little bit out of order. Okay, and then the C3, which was given as part of the front side of this homework, and for one of your problems that you had to use. But the C3, the angle would be 120 degrees, right? 120 degree rotation, a circle divided into three parts. And so if we operated using the sines and cosines, we end up with values of -1/2, -√3/2, 0 for our first row, √3/2, -1/2, and 0 for the second row, 0, 0, and 1 for the third row. All right. So these are our three transformation matrices. Now, in this case, there's something right away we see different from the C3v case that we were looking at with water. In particular, the C3, right? So with water, if you look back in your notes, we would say, oh, there's all these zeros, so we can think of these as independent. This means that the x coordinate here is independent. And I mentioned this last class. When we look at the C3, we see that's no longer the case. So we're not going to be able to block diagonalize quite the same way. What this is showing me is that x and y are dependent on one another. Or they transform together. Another way to think about it. You cannot affect the x coordinate of an atom without also affecting the y coordinate, is what this is showing you when there are non-zero elements on the off-diagonal set. So if we have to do it for the C3, we're going to have to do it for the other two matrices as well. We're going to have to treat them or group them, block diagonalize them exactly the same way. So in class on last time, we got 3 small matrices out of this process, right? Because we had all zeros on our diagonals. Today we're only going to get 2 what are known as the irreducible representations by identifying the trace. So what I'm going to do now is I'm going to sum the diagonals of these respective smaller matrices that we looked at within within each of these 3. So these are what we call our gammas. So gamma 1 has a character for E, and I'm going to rewrite them in order now, C3, C2. Even though I did the C2 first, when we list out a character table, the highest n comes first. So the character of E is 2 from this first matrix. Okay. The character of C2 is C3, I got to skip over here, is -1, and the character of C2 is -2, right? So what I've done is just added the diagonal elements. Okay. For the second irreducible representation, the characters are 1 from E, 1 from C3, and 1 from C2. This one, now, it's kind of maybe a little disappointing, right? Because we know that every group has to have an all symmetric, and all ones. So when you get it out of this process, it kind of denies you the chance to get an easy one that you have to find on your own. Because there's a third irreducible representation here. And I know that because one of the rules is that character tables are square. There are 3 classes of operations here, right? And so we must have 3 unique irreducible representations out of this. So that it would have been nice if this one was not 1, 1, 1. We would have known immediately what the third one was, all ones. Okay. So now we're going to have to figure. Did I do something wrong here? Okay. I'm sorry. I did something. There's something wrong here. The C2, because it's a perpendicular C2, the X actually, I just looked at my key here, does not change. This isn't the main C2. This is perpendicular to what's been defined as the Z-axis. So the X coordinate would not change, and that's actually going to make this value 0 then. Yep, that didn't match up. But what does change is, good. My little explanation now has come to fruition. What does change is that the Z. Okay, again, this is perpendicular because our molecule has a Z-axis that is also its C3. So a perpendicular C2, just so you understand how I'm coming up with this, a perpendicular C2 is going to take an atom's Z coordinate and rotate it down and make it -Z. And it's going to take its Y coordinate, if it's out here, if we had an atom out in front, and it's going to move it back behind the board. But its X coordinate, how far left or right it is, since this is the X axis, is not going to change. So it's a little bit tricky. Okay, sorry about that. I got a little bit ahead of myself. Forgot that not all C2 matrices are the same because of if they're perpendicular to the primary axis. But now our characters all make sense for us here. Okay? All right? So these are the 2 irreducible representations, okay, that come out of analyzing the transformation matrices. Okay? Now, the third one, now it is quite simple now. The third gamma, gamma 3, must be 1, 1, 1 for E, C3, C2, because we need an all-symmetric, irreducible representation. Irreducible rep. Okay? So then, in this case, it did end up being easier. However, if it wasn't, the way that we could figure out what the third would be is to use some of those other rules of the table. The fact that the sum of the squares of the first column have to equal the order. Now, I didn't include the coefficients here. There are 2 C3s and 3 C2s, so the order is 6 for this group here. All right? And so you'd have 4 squared plus 1 squared plus 1 would be the, you could tell now would be the first one. And then the cross product of any two would be equal to 0. So a good strategy, let me demonstrate a little bit of that. A good strategy for figuring these out, E2C3, 3C2s. So we have our gamma 1, which is 2, negative 1, 0. Our gamma 2, which is 1, 1, negative 1. And let's say we didn't know our unknown gamma. We would put in variables, A, B, and C. Again, we can use, I think it's like rule 4, okay? The 2 squared plus the 1 squared plus A squared must equal 6, which is the order of our group, 1 plus 2 plus 3. So this is A squared equals 1, so A equals 1. Okay. Then, now that you have A, you want to do a cross product. It's a little bit easier if you do the cross product of 1 and 3, because you see that one of your things will drop out because of the 0. All right? If you do the cross product of 2 and 3, you're going to have 2 variables, unknown, B and C, in there. Okay, so you're going to get simultaneous equations. So there's a little bit of, rather than just rushing in and just picking anything at random, as you practice a little bit with this, you learn that you definitely want to choose irreducible representations that have zeros for your doing these cross products, because they will eliminate one of your unknowns, and you'll get to your unknowns faster. Okay? So if I did the cross product of 1 times 3, we would have 1, the coefficient of E, times 2, the character under E, times A, which we now know is 1, plus 2, the coefficient of the class C3, times negative 1, the character for gamma 1, times B, plus 3 times 0 times C. And that all has to equal 0, because the cross product of any two of the irreducible reps in a group is 0. They're orthogonal. Okay. So what's this give us? 2 minus 2b equals 0. 2 equals 2b. b equals 1. And now you can go back and do the cross product of 2 with 3 to find C, because you now know A and B. And so you'd have 1 times 1 times 1 plus 2 times 1 times 1 plus 3 times negative 1 times C. Okay? Coefficient from the very top row times the character value for the first irreducible rep times the character value for the second irreducible rep. And I already know the values of A and B, so that's what I've put in for these positions here. Okay? So this gives, and this equals 0. So you get 1 plus 2 minus 3c equals 0. 3c equals 3. C equals 1. So even though we already knew we needed the all-symmetric irreducible representation, we can do the math to prove it, or to find it in some other situation where we may not have it. Okay? Okay. Any questions there? Okay. Would you prefer to do another one of those? You want to see that done one more time? We'll kind of work through it, or you get it now? No one wouldn't hurt? Okay. All right. You think you got it? All right. Well, you can work through it independently if you want to. All right. But I'll guide you through. This is exercise, or sort of in the text. Right. There are these exercises embedded. They're not the homework problems at the end, but this is exercise 4.6. Yeah. Question, Kristen?
The last problem on the bottom.
Uh-huh.
Did we fill that one in or no?
Oh, identify the, is that labels? Yeah, we didn't get to the labels yet. So once we, that's going to be part of what we talk about this morning. Yeah. All right. So hang on to it still. Not quite ready to collect that. Okay. All right. So I'm going to try to duck and see if this thing comes down. It doesn't seem to want to find me down here. Okay. That's kind of weird about that. If anybody not from your college ever watches these videos, they must be like, what the heck is going on? Anyway, so this is exercise 4.6 in your textbook, and it asks us to develop the character table, like we just did for another group, another small group, for the C2H group. Okay? They give us a particular molecule, the N2F2, in a trans conformation. But again, the molecule isn't so important as long as we know what the elements are of the C2H point group. E, of course, everything has E. The highest axis of rotation is principal C2. All right. There is a center of inversion, I, and there is a horizontal mirror plane, a sigma H. Okay. So we want to list out our transformation matrices, 1, 1, 1 on the diagonals for E. Being a principal C2 now, we go back to what we developed last class, -1, -1, 1 on the diagonals for the main C2. Center of inversion, every coordinate comes through the center and is pushed out in the opposite direction, so every coordinate gets flipped, right? -1, -1, -1 will be the diagonal elements of this one. And then sigma H, we looked at a sigma H last class. A sigma H horizontal means it's perpendicular to the plane. So here's your main C2, thought of as the Z-axis, right? This is going to be a sigma H. So what's going to change is, another way to figure these out, by the way, is to use like not necessarily a molecule, but like a little arrow. So before, and then if you reflect this, afterwards it's reflected down like that. The only coordinate that's changed is the Z, okay? It's now negative of Z. So it's got values of 1, 1, -1 on its diagonal. So looking at these, X is independent of Y, which is independent of Z. Okay? Again, I'm making that conclusion because we don't have what we had for our C3 over here, where there were off-diagonal elements on any kind of rotation or any transformation. Right? Every row has just one number in it. And so that means that the coordinates of an atom are only dependent on the initial X, Y, or Z, not an and there. Okay? So these can all be block diagonalized, and we're going to get 3 of the possible irreducible representations. So we're going to have E, C2, I, sigma H. Our first irreducible representation is 1, -1, -1, 1. Okay? I just took the first member of each matrix. Our second irreducible representation is 1, -1, -1. Wait, did I do something wrong? Because those can't be the same. Oh, okay. Yep. That's okay. They give us the same. Okay, so actually it's not quite as helpful as we want it to be. What this shows us is that x and y transform the same way. Okay, so it doesn't. They're not. These are not unique irreducible representations. It's just that x and y behave exactly the same way. They're not linked. They just behave exactly the same way. Okay. All right, and then gamma 3 would be 1, 1, negative 1, negative 1. So in reality, we have only 2 of the, how many should we have? How many irreducible representations? How many rows should this character table have? 4, because it has 4 columns, all right, of operations. Okay. Let's just, I'm just going to put a line through this one, okay, so it doesn't confuse us anymore. If you get ones that are identical, they're not unique, all right? So you need 4 unique irreducible representations. Our next one we should be able to get, we'll call it gamma 4. We haven't yet identified an all-symmetric irreducible representation, right? So we know that this one should be here. Okay? All right. And then our last one we would have to develop using the same processes. We'd have an A, a B, a C, and a D. Okay? The order of this group, H, is equal to 4. 1 plus 1 plus 1 plus 1. Everything has there's just one of each of these operations. Okay? So the first rule that we can use is the sum of these squares here, and it should be pretty obvious that if you take the 1 squared for gamma 1 plus 1 squared for gamma 3, 1 squared for gamma 4, plus a squared equals 4, you get that a equals 1. Okay? Now, the rest of this is going to be a little bit more of a puzzle, to be honest. There are no zeros that we can use to reduce the number of variables at play here. So we're going to develop, if we pursue the characters B, C, and D, we're going to develop a system of simultaneous equations. So let's see. 4 times 5 would give me all positive stuff. All right? You don't have to do it in any particular order. 4 times 5, and all these coefficients are 1. So I'm going to save myself a little bit of trouble. I'd have 1 plus B plus C plus D equals 0. Okay? I can't do much else with that right now. Okay? And then you have to do things like, okay, 1 times 5. 1 times 5 is going to be 1 minus B minus C plus D equals 0. Okay. So one thing you could do here is now you could substitute one of these into the first, and you'd go from 3 down to 2. Okay. But you're still going to need one other. You're going to have to do like gamma 3 times gamma 5. So that's going to be, again, 1. 3 is going to be plus B minus C, and then minus D equals 0. Okay. So now this is just like it's a little puzzle. All right, you just kind of have to work your way from one to the other. All right. Sometimes you might see a pattern that lets 2 things drop out. Okay. If we added these 2 equations, both the C and the D would be eliminated. Okay. So if I add these 2 equations, I would get that 2 plus 2B equals 0. So that means that B equals negative 1. Okay. All right. So now that I know what one of the values of B is, if I go with these two equations, then I see that they have opposite signs of D. And I can add those two together. But I now know what B is. So this is actually 1 plus 1. So it's 2. I'll rewrite these for you real quick so that you're not quite so confused. This is actually now 1 plus 1 minus C plus D equals 0. This is now 1 minus 1, so 0. So this is now negative C minus D equals 0. So if you add those two together, you end up with 2 minus 2C equals 0 because the D's have opposite signs. And so 1 equals C. Okay. And then lastly, you can use any one of the remaining ones now to figure out your D value. Okay. So you could go back up to any one of these. I could do this because D would just equal the 1 plus B minus C. So that's 1 minus 1 minus 1. So D is equal to negative 1. And you should check, you should put it into this right here because this new one that you developed cannot match any of the other ones that you had. So we had 1, negative 1, 1, negative 1. And so this is actually, often the case. You've got all positives, and then you've got 2 negatives in the middle, 2 negatives at the end, and 2 negatives split out, all right, in those 3 positions. So you think about where you can put the negative ones, how they could be shuffled out. That's going to be the way they get arranged. Okay? All right. So we just built another character table, came up with the missing representations. All right, now to address Krista's question earlier about the labels. These labels in the character tables are assigned, okay, and they're given names. Now we're going to go through a real quick set of rules for what the names are, but once we understand how the names get assigned, when we then hear one of those names, it tells us a little bit something about the irreducible representation that's being identified. Okay, so I said names, more properly known as the labels of irreducible representations. Okay. All right, these begin on page 99, by the way. This is like one of the additional features of the text. All right, so if the dimension, okay, equals, the dimension, remember, is the E character. Okay, so it's the first value of the irreducible representation. Okay, so if the dimension equals 1, there are 2 possible labels. Okay, A, we use A if the highest Cn also equals 1. We use B if the highest Cn equals negative 1. Okay. Now, remember that saying something equals 1 means that it is symmetric with respect to this operation. And negative 1 means anti-symmetric. That you change something's coordinate. So that's what plus 1s mean and what minus 1s mean in character language. All right? All right. If the dimension equals 2, the label is E. And if the dimension equals 3, the label is T. So that's it. Those are the possible labels for irreducible representations: A, B, E, and T. And then there are a series of subscripts that are assigned. Okay? All right. The subscripts come in different categories. There are numerical subscripts. We use 1 if, okay, if the irreducible representation is symmetric, again, with respect to, okay, a perpendicular C2. You use the subscript 2 if it is anti-symmetric with respect to that perpendicular C2. If no C2 exists, if no perpendicular C2 exists for the molecule, okay, then 1 is used if the molecule or if the irreducible representation is symmetric, okay, for a sigma V, a vertical mirror plane, 2, again, if you're anti-symmetric for that same vertical mirror plane. Okay. So 1s and 2s are indicating symmetry with respect to perpendicular axes or a vertical mirror plane. You wouldn't do both. If you had the perpendicular C2s, you would base this decision on that. You wouldn't then also look at a sigma V, and that could confuse you. Okay, so. I'm trying not to erase these gammas that we had here so we can put labels on them. All right. And then there's another layer of subscripts. If the group has center of inversion, I, okay, we use 1 for symmetric for I, and 2 for, we use G and U. This is when we move away from numbers. G and U. And these are meaning the words gerade and ungerade, all right? I believe they're German, which means symmetric or not symmetric, all right? So that's where those labels come from, all right? Gerade and ungerade. And then sometimes we seldom will have to assign these, all right? But then there are also primes, so not subscripts, but now superscripts. Primes are used if a sigma H exists, okay? Then we would use a single prime, or what looks like an apostrophe, for symmetric, and a double prime, which would look like quotation, for anti-symmetric. Okay. And it even says this isn't used too often. It lists just four groups that you need to worry about this being used in. So we've got a bunch of irreducible representations up. Let's go through and label them. These were the 3 from our homework. This was, again, a 1. Fill that back in. We erased it, but we found that it was all 1s. So gamma 1 that we developed from the what we sometimes would refer to as degenerate or linked coordinates, x and y. It has 2 as its dimension. So it is an E, okay? It's E, okay? All right? Now, don't get too carried away and think, oh, I have to put a subscript on there. No, you don't have to put a subscript onto there, okay? And in fact, we don't have a number for a subscript in this case, right? Because the subscript 1 or 2 is relative to a perpendicular C2, not to what's going on with the C3 next door, okay? So the highest principal axis kind of loses its contribution to the naming when there's an E, okay? Is that a question, Josh?
So the labels will go next to the gamma symbol?
Yeah, they would actually replace the gamma symbol. In a real character table, we would then erase the gamma. You have like a temporary name, okay, until we come up with the official name for that, okay? So this E is describing 2, -1, 0. Okay. Gamma 2 has character dimension 1 for E, which means it could be A or B. So now we have to look at the highest CN, and it's 1 for C3, so that makes it an A. And then we need to look at the next layer, all right, because both of these, gamma 2 and 3, you see they're both A, because they're both dimension 1 and symmetric with respect to the C3. So now we need a distinction between these two. We need the next layer, okay? And so we go to the perpendicular C2. The gamma 2 is antisymmetric, so it's going to be A2. The gamma 3 is symmetric, so it's going to be called A1. Right? All ones are always going to be pretty much called A1 or AG, all right, if there's a center of inversion, as we have over here. Let's come back and label these now. These are all going to be either A's or B's, right? Okay, because all of them have dimension of 1. So what we call gamma 1 is going to be a, can I fit it in here? Yeah. It's going to be a B because it is -1 with respect to C2. And it is antisymmetric on inversion, so it's actually the BU. Gamma 3 is A because it's +1 for the C2. -1 for I, so it's AU. Gamma 4, +1 for C2, +1 for I, so now we see it's a unique AG. Gamma 3 is B, -1 for C2, +1 for I, so it's BG. And so just like you should have unique sets of characters, you should be able to arrive at a unique label. If you come up with two that are the same, then you might need to go one more row over and consider the next, operation, because it might give you the prime or something like that. Okay? There are possibilities, we've used up all our examples here. There are cases where you need both a number and a letter, like a G or a U. Okay? If you have a perpendicular C2 and a center of inversion, you're going to get a number for the C2 and you're going to get a letter for the center of inversion. Okay? So that's how these work. All right. So where we're headed with all of this next class is the connection between group theory and vibrational spectroscopy. All right. And I mentioned this last time, that infrared spectroscopy, how many peaks a molecule shows in its IR spectrum, is directly predicted or connected to group theory and all of this. But before we can really explain that, I need to explain what's known as reducing, okay, representations. Last class for the C3v case, right? When we developed that character table for the C3v, just to remind you, in developing the C3v table, we examined what's called the trace of each of the transformation matrices. And we developed this thing that was C2. We had a sigma V X Z and a sigma V Y Z, or called sigma V prime. All right? And we got a total value, all right, by summing up those diagonals of 3, -1, 1, 1. Okay. So when you see representations like this, okay, this is a combination. All right, so we already know this. We broke this down by looking at the 3 different matrices. We broke it down. But for now, it's going to be another, we can get a little more mileage out of this in learning about this process called reducing. So this representation is a combination of the irreducible representations, right? The fundamental elements, symmetry elements, the irreducible representations of the C3v group. We can find that combination, okay? So we can find what combination by reducing it. To reduce it, we need the complete character table. So the character table, A1, A2, B1, and B2 are the 4 irreducible representations. Okay? I'm going to go down the columns, they're all 1s, 1, 1, 1, 1. Then they're 1, 1, -1, -1. 1, -1, 1, -1. And 1, -1, -1, 1. So gamma 1 up here in the top row is some combination of these. Now, we actually already know what it is because we built this character table last class. But to show you this process of reducing, here is how we come up with the contribution that each makes. Okay? So in other words, gamma 1 equals some n value times A1 plus a different coefficient, well, let's call it NA1 plus NA2 times A2 plus NB1 times B1 plus NB2 times B2. So what we need to do is find the coefficients. The n, right? The nx values. Right? N, for whatever thing, equals 1 over the order h plus, and it's a lot like the cross product, the class coefficient times, all right, the gamma character times the actual irreducible representation character. Remember that chi means the character. The 1, 2, -1, 0, the number that's in there. Okay? And then you repeat this. I missed my sum. Sorry. You sum across all the irreducible representations. It's a messy formula. It's easier seen, I think, with the actual examples. But if you want to know what you're doing, that is what we're actually doing. Okay? So to figure out how many A1s are part of, or if at all, A1 is part of this, 1 over, okay. Now I left off, I think, nope, I didn't. Our group is, for C3v, our order is 4, right? So we have 1 over 4. Now, E is coefficient of 1 times 3, the value of gamma 1, times A1's value. Okay? So I'm going to, in a second I'll shift back over there. I'm going to take this number in the top row times this number times this, plus this, plus this, plus this. That'll tell me how many A1s. Then I'll repeat this for A2. I'll just jump down. The only thing I'll change is it'll still be 1, 3, but now I'll jump down and take the A2 character last. All right? So that's all. That's what you have to do. Okay? So that was 1, 3, 1 plus 1 times -1 times 1 plus 1 times 1 times 1 plus 1 times 1 times 1. Okay? Now, the beauty of this system, you must get whole numbers, okay, to find the coefficients. These coefficients must be integers. If you can't get some multiple of 4 out of this combination here, you've made a mistake, and you must figure it out, okay? There's no going to be any rounding or anything. It's going to be a whole number. So what do we have here? We have 1/4 of 3 minus 1, so we're down to 2, plus 1, back up to 3, plus 1 up to 4, 1/4 of 4, so we have 1. All right. What changes when we go to A2? The only, and this is where it gets kind of nice. The only thing that'll change, if you rather than thinking about what am I doing, the only thing that'll change will be these two numbers, right? See how A2 is just like A1, except that these two numbers are -1. So I already know that this is going to be 1 times 3 times 1, plus 1 times -1 times 1, plus now it's 1 times 1 times -1, and 1 times 1 and -1. So that's 3 minus 1 minus 1 minus 1. That's 0. Now. So there are going to be no A2. Nothing with this A2 symmetry, okay, contributes to this reducible representation that we have. Then we have N for B1, 1/4 of. Well, and again, we can think, how is B different than A? So the second and fourth values are going to change sign. So it's really going to be 1 times 3 times 1, plus 1 times -1 times -1. Back to the original 1, 1, 1. And then 1 times 1 times -1. 3 plus 1, 4. Plus 1, 5, minus 1, 4. We still have a 1/4 of 4, so we've got 1. And I'll write the last one up here. I'll tuck this in up here. B2, okay, equals 1/4 of. Now the two middle terms, the third number in the two middle terms is going to be negative. So 1 times 3 times 1 plus 1 times -1 times -1 plus 1 times 1 times -1 plus 1 times 1 times 1. That's equal to 1/4 of 3, 4, 3, 4. So 1. Okay. There are other checks in place here. 1, you have to get an integer. 2, you have to account for the total dimension of your gamma. So 3 is our dimension, right? So we have 3 things. We have our gamma equals A1 plus B1 plus B2. So that's 3. You know, each of these has a dimension of 1, as each of these irreducible representations, their first character is 1. So we know that's going to add up to the 3. That's the first. Okay. If you have E's, it's tricky for you because an E accounts for 2. Right? And so you'd have to remember that. Right? If E was part of this group, A1 plus E would give us the 3 that we'd have. All right. So it's not that you have to have 3 or more 3 things. They have to add up to 3. Okay. So this is what's known as reducing a representation. Okay. Finding out what components, in other words, are part of the the aggregate that you're looking at, okay, or the total. Okay. All right, let's try another one of these. So let's say that we're still in the C3v Point Group. Okay. Well, maybe I could find another example that wouldn't be C3v. Let's see. There we go. C3v Point Group instead. Here's our gamma. There are 3 operations, E, 2 C3s, and 3 sigma Vs. The gamma has a value of 12, 0, 2. There are 3 members of the C3v Point Group. Go back and find them because they're part of an example from the other day, I think. They are A1, A2, and E. A1, of course, is 1, 1, 1. A2 is 1, 1, minus 1. E is 2, minus 1, 0. So let's reduce gamma into its components. Or what combination of these 3 irreducible representations that describe how the molecule transforms, okay, in this C3 point group, what combination of these 3 elements is being put together to make this representation up here? Okay. So what's the order? Shall we start with that? The order is 6. 1 plus 2 plus 3. It's the coefficients, the sum of the coefficients. Right? So the n, the coefficient of A1, is 1/6 of top value times the gamma value times the irreducible representation value. So that's 1 times 12 times 1 plus 2 times 0 times 1 plus 3 times 2 times 1. 1/6 of 12 plus, this is 0. Okay, 12 plus 0 plus 6 is 18. Get a whole number 3. Okay. N of A2, 1/6. The only thing that's going to change is the last number here. So you know that this is still 12, this is 0, and then this is 3 times 2 times -1. So you get 1/6 of 12 minus 6, or just 6. So there's 1 A2. And then E, 1/6 of, now you kind of have to redo it here, 1 times 12 times 2, because the dimension of E is 2. We still know the middle value is 0 because of the 0 from gamma. And we know the last value is 0 because there's a 0 in the E irreducible representation. So this is 1/6 of 24, which is 4. Okay. Now the dimension of gamma is 12, right? These three numbers only add up to 8, but this is a degenerate. This is describing 2 coordinates transforming at a time, right? So that 4, because it's corresponding to E, so gamma is equal to 3A1 plus A2 plus 4E. Okay? 3A1 plus A2 plus 4E. Right? And so that doesn't necessarily add up to the 12 that you're thinking about here for gamma's value, but remember the E has a dimension of 2, and so really if you took 4 times the 2, that's 8, 9, and then 12. And you see that it equals then. Right? So there's a little built-in check that you've accounted for the dimension of E here. Okay. All right, so we're going to do plenty more of that. That's going to be in the context of when we start to talk about the spectroscopy stuff next class. All right. Do one more thing here. All right. Let's consider. Try to draw as best as I can. X, Y, and Z. Here's X. Z is typically now our up, down, and Y would be our thing coming out of space. Okay. Okay. Suppose we had some atom out here. Okay. Actually, I'll try to draw it. So that it looks like it has an X, a Y, and a how do I get perpendicular to Y? There we go. Okay? Did I do that right, or should it come over this way? No. There we go. Okay? So there's this atom that has an X, a Y, and a Z coordinates, none of which are 0 right now. Okay? None of which are 0. Okay? If this molecule underwent a C2, okay, inversion, a C2 operation, right? We know that this would swing around, okay, the Z-axis, and it would end up back here. And we know that it would have negative X, negative Y, and positive Z as its new coordinates there. That's what we looked at last class, and we used that to develop those transformation matrices there. Okay. To help us think about vibrational spectroscopy, we're going to have to start to think about how every atom transforms, okay? But rather than actually having to draw these pictures and figure out everything, there's a neat little system that we can do, okay? Suppose that you just had the three sort of coordinate vectors like this, x, y, and z. Oops, sorry, I interchanged my y and z, x, y, and z. Okay? And that this coordinate system underwent a C2. The way it would look afterwards would be x would be pointing in the opposite direction, z would be pointing in the same direction, and y would be pointing in the backwards direction as well. Okay? So this coordinate system here would be transformed. A classic way to think about this is to use your right hand. My right hand is describing this right here. And then to rotate it 180 degrees, this is the result. You see here? Okay? So I want to apply some rules to what we just did here to help us figure out the how this impacted this three coordinate system here. Okay? So any coordinate vector that is unchanged will add 1 to the representation of this operation. Okay? So it's not going to be just one atom that moves when we perform a symmetry operation, right? There's going to be multiple atoms. In this case of a C2, the Z didn't change at all, right? Took my fingers, rotated them, my Z finger index is exactly in the same position. So it will contribute 1 per each atom that undergoes that. All right? We'll talk about multiple atoms next. Okay? If a coordinate vector, okay, points, let's say, in the opposite direction after the operation, it adds -1 to the representation. That would be the case of x and y, right? Think about your x vector. It's pointing so many units in what looks like our right now. But then after this rotation, it's now pointing that same number of units, but in the left. So in vector language, it's completely negative of what it was. All right? Y is the same way. Pointing straight out right now, then it's pointing backwards, okay? So it's going to contribute -1. Okay? One last case. If a coordinate vector ends up on a different axis, it adds 0 to the representation. Okay? So if we had a 90-degree rotation, if I went back to my original one and did a C4, my Z would be unchanged. My Y would be where my X was, and my X prime would be sort of the opposite of my Y. So Z would contribute +1, but Y and X would each add 0 because they end up on another vector's sort of direction. What we've really just done is applied like sines and cosines to vectors, but in a much simpler fashion. Okay? When you rotate something 90 degrees, right, the is it the cosine of that that's equal to 0. All right, so there's no component of this vector after a 90-degree rotation that's still in the original direction. Okay? So what these numbers are, +1, 0, -1, are really saying what component of this vector, after we rotate the atom or do whatever it is, remains in the same direction here. So it's easiest if our angles are multiples of right angles. Okay? If we're talking about a 120 or something like that, right, then this goes, then it's like -1/2. Okay, so that's a little trickier. So we'll see that we'll avoid most of those cases, actually. Right? So when we start to have multiple atoms and we want to figure out how an entire molecule transforms, this is going to be the easiest way to do it. It's to slap a 3-coordinate vector on every single atom and then rotate the molecule according to the operation. Now there's one additional rule. And we'll get it, I'll remind you, I won't write it now, but I'll remind you. If an atom moves, so if I'm an atom over here, here's my x, y, z, but then this molecule rotates and I move over here, okay, none of my vector is originally where it was, right? I mean, it was originally anchored over here. Now it's all over here. None of it remains over here, or over here where it started. So it'll contribute 0. That's another case where you would add 0 to the what's called the representation of the molecule. All right? And so we're going to look at that next class. All right? I will collect your homework that was due today. And I have a homework worksheet for you that I'll pass out in just a second. And I would like to have a quiz on next Tuesday, going over the labeling stuff, going over the reducing stuff maybe, going over finding a missing representation. So it'll be mostly the character table stuff that's on the quiz next time. All right? So I'll shut off the video and collect up your homework and pass one out. See you later.